In this set of problems, what we are discussing, or questions, what we are discussing is the properties of measurable functions. So this is also part of to have a deeper understanding of measurable functions before we go into some spaces of measurable functions and their properties and so on and so forth. So for one has to be a little bit deepen his understanding of measurable functions and separate this from the classical approach to functions as we learned them in real analysis. I'm talking about, of course, continuous functions, lower semi-continuous functions, etc., etc. Okay? So the first problem in the first one, or the first question, okay, we have two functions which are, so we have f, g defined on a closed interval into R, and we're assuming that they are continuous, okay? This is very important assumption on the entire interval AB. And we assume also that f is equal to g almost everywhere, okay, on AB. Okay, so now what we are going to do is we are going to take a new function, h, from AB into R, defined by h of x equal absolute value of f of x minus g of x. And again, using the properties that f minus g is continuous as well as the absolute value is a continuous function, composition of two continuous functions is a continuous function. So this will tell us that h is indeed continuous. So h is continuous. Okay, so now we look at the set of x in AB such that h of x is greater than 0. Okay, so basically we know that h is equal to 0 because f of x is equal to g of x almost everywhere. Almost everywhere. Okay, so this tells us that this set has measure 0. Okay, but since h is continuous, it is also open. Continuous, O is open. Okay, so if O is not empty, okay, assume that O is not empty. So in this case, we know that O will contain a non-degenerate open interval, a non-degenerate non-empty open interval. Of course, if you have a non-empty open interval, it is non-degenerate. But I'm just stressing the fact that the length of this interval will not be 0. So this is a contradiction. Because the length of the interval will not be 0, which implies that the measure of A, which is bigger than the measure of that interval, so since the measure of A will not be equal to 0, it's going to be greater than the measure of that open interval inside, and therefore we have a contradiction, okay? Which tells us that H is equal to 0 everywhere, and therefore F is equal to G. Okay, so now the question is this true if we replace the open interval? So question, is the conclusion true if we replace the open interval by a measurable set E? Okay? And the answer is no. Okay? Example. So we're going to take this function So this is minus 1 and 1. This is 1. And this is f. So this function here, f, is equal to absolute value of x if x between minus 1 and 1, and 1 if x greater than 1, minus 1 if x is less than minus 1. Okay? So what happened? We take g of x, so this is g of x equals to 1 everywhere. So what happened now? So of course we need the set E. Set E will be 0 union the interval 1, 2, or whatever. It doesn't matter. We can take 1, 2, 1, 3, or 1 plus infinity. It makes no difference whatsoever. Okay? So if we take E0 equal 1, 2, then we have f of x equals g of x for x in E0. Okay? Obviously, E minus E0 is equal to 0 is a point, has measure 0. So f is equal to g almost everywhere on E. Okay? Obviously, but f of 0 is different from g of 0. Of course, 0 belongs to E, so they are not the same, though f and g are continuous on E. They are continuous everywhere, even on R, so they are continuous also on E. So this conclusion is false. The second question, okay, we're taking two measurable sets, so A and B are measurable, subset of R. And we have F, which goes from A union B into R. Okay? So what we're going to do, we're going to take from F, we're going to generate two functions. The restriction to A and the restriction to B. So I call them f sub A and f sub B. So such that x gives me f of x, such that x gives me f of x. So we call them the restrictions, okay? And in fact, it's very simple to see that fa and fb, they inherit a lot of properties of f. What's interesting is the fact that f is measurable. F is measurable if and only if fa and fb are measurable. Okay? So, assume f is measurable. And let us prove that fa and fb are measurable. So, the proof is similar because of symmetry of A and B, the role they play. So I'm just going to show that FA, in fact, is measurable. For that, let us look at the set. So fix C in R. And look at the set X in A such that FA of X is greater than C. So we want to show that this set is measurable. Okay? So what is this set? This set is X in A union B such that f of x greater than c intersect A. Okay? Because fa of x is equal to f of x. So now, what do we know? We know that this set here is measurable because we assume that f is measurable. A is measurable by assumption. The intersection of two measurable sets is measurable. Therefore, f sub a is measurable. And as I said, by symmetry, we obtain also that f of a similarly we have fb is measurable. So now we go to assume the converse. So assume fa and fb are measurable. Okay? So we want to show that f is measurable. Let's see. And look at the set of x in A union B such that f of x is greater than c. It's very easy to see that in fact this is x in A such that f of x greater than c union x in B such that f of x greater than c, which is equal to x in A such that f a of x is greater than c union x in B such that if b of x is greater than c. So now we assume that fa and fb are measurable. Since fa is measurable, this set will be measurable. And since fb is measurable, this set will be what? Measurable. So the union of two measurable sets will be what? Measurable. Therefore, this set is measurable, which implies that f is measurable. So the question now becomes, is this true if measurable is replaced by continuous? So in other words, is this is the question, is f continuous if and only if, fa and fb are continuous? And the answer is no, of course, because you can glue them. A and B, you can glue them to give you an interval. For example, you can take, so you go from 0 to 1, okay? And from 1 to 2, so you see this function f is discontinuous at 1. But if you take the restriction to 1, 0, 1, and 1, 2, but 1, 2 has to be, so we take A equals 0, 1, but for B, you have to remove 1. So the restriction to these two subsets is definitely what? Continuous. So FA and FB are continuous. So this is, you can come up with different examples. You need to glue two pieces with the jump. So this gives you a discontinuous function globally, but its restrictions will be what? Will be continuous. Next, we want to prove, suppose a function f is measurable on domain, except domain, and it's continuous. So here, 3. So we have f defined on a measurable domain, E, and we assume that it is measurable, and its domain is measurable. Okay, and we assume that there exists x1, x2, xn, finite number of points, they are different, of course, such in E, such that f restricted to E minus x1, xn is continuous. So it is continuous everywhere except in a finite number of points. Okay, so it's interesting what you do. So you want to show that f is necessarily measurable. Oh, I'm sorry. Yes, yes. Here, I'm sorry. I'm sorry. That was the question. So we want to show, in fact, that f. So we only have, um, we only assume that f is defined on a measurable domain, but continuous everywhere except in a finite number of points. So what you do, you look at, for example, the set E0 equals E minus this finite number of points, which is exactly E intersect the complement of x1, xn. Okay, so this set is measurable. Okay, so remember x1, x2, xn is finite. The finite sets are closed. The complement will be open, and now open is measurable. E is measurable. The intersection of two measurable sets is measurable. So E0 is measurable. Okay, and we know that the restriction of f to E0, okay, which is defined on E0 into R, okay, so this function is continuous. Therefore, f restricted to E0 is measurable. So now fix C in R and look at the set x in E such that f of x is greater than C. So this would be exactly x in E0 such that f of x is greater than C, okay, union, okay, the set of xi's such that f of xi's is greater than C. Okay? So what happened? Since the restriction of f to E0 is continuous and is measurable, this set here will be measurable. And this set here is finite. Okay? So this one is finite. Therefore, it is measurable. It's closed. And this one is measurable. And therefore, you have a union of two measurable sets is measurable. Therefore, this set here is measurable. Which implies that our function f is measurable. So the conclusion is valid. Next problem, 4. We're looking at a function f which goes from R into R. And we assume that for every C in R, f inverse of the singleton C is measurable. Question, is f measurable? Okay. The answer is, in order to understand the answer is no. But in order to understand this, let us just analyze this business. Okay. So first, remark. Let us do a simple remark here. Okay. Assume f is 1 to 1, injective, in other words. Then f inverse of any singleton is either empty or reduced to 1 point. Reduced to 1 point. So in this case, obviously, it's going to be measurable. Okay? So the assumption is satisfied. So this tells me that if that's the case, then any one-to-one map should be what? Measurable. Okay? That's the idea here. So basically, as an implication, if we assume that the conclusion is true, okay, this will imply that any one-to-one map from R to R is measurable, and the answer is no. Okay, so how do we build a function that is not measurable? Of course, the way to do it is you take a set so take E a subset of R, non-empty. Okay, And look how we can define a function f from R to R, okay, such that f inverse of, or the set such that, such that the set of x such that f of x is greater than 0 is exactly E, okay, and is one-to-one. So you see, given any subset of R, non-empty, I'm going to build a one-to-one map such that all the points where the function is positive is exactly E, okay? So how do we do this? So take, for example, take f of x equal ex if x belongs to E, and minus ex if x does not belongs to E. Okay? So I leave it to you to check that this function is one-to-one. And if you look at the set of x such that f of x is positive, we're going to find exactly E. So if indeed one-to-one maps were measurable, then basically any subset of R is measurable. And we know that's not the case, that there are sets which are not what? Measurable. Right? We build one. Huh? So this tells us what? That not every one-to-one function is measurable, and therefore the answer to the question is in the negative. Okay?